All right, thank you and good afternoon, everyone. So yeah, I will be presenting LinkEdge, an open source solution for the integration of MLOps with IoT Edge. This was done by Solita in collaboration with the University of Oulu. So just to give you a brief introduction of what the project is about, our aim of this project was to research, design, and develop a solution that enables the integration of MLOps practices with edge devices. So just to kind of take you through how we designed this solution, maybe I should move this way. Yeah. So this is the architecture of our system. So as you could see, we have two layers called the cloud layer and the edge layer. And the main component of this cloud layer is this thing called the MLOps CI pipeline, which essentially takes in data from our edge devices. It produces a machine learning model, packages into a Docker container, and pushes it into a registry, which is then pulled by our edge devices. And the reason why we use Docker to package machine learning models is because machine learning models can have various different formats, and having Docker or containers offers a more generalized way in which we could package these models. And second, containers already have good support for CI/CD practices. And third, most devices running on doing inference, most edge devices doing inference already have good support for containers, because they kind of run on Linux kernels for the most part. So apart from that, we also have this component called a performance monitor, which essentially takes in the model performance. And if this performance falls below some certain threshold, it will then re-trigger our CI pipeline, which will then rebuild a newer model with newer data, again, package it into a container and have it be available in the model registry. And this model registry, you can see, sits between these two, the edge layer and the cloud layer, because we wanted our users, our developers, to have the option to decide whether to have this registry on the cloud or maybe somewhere on-prem, which is closer to the edge device. Apart from that, we also have a fleet of edge devices. So what goes on in these edge devices is this architecture. I'm not sure if it's clear to you, but there are a bunch of components here. But the main component that we need to consider is this edge controller, which essentially is the kind of like the glue that puts all these things together, where it manages the communication between all of these components. And our sensors communicate with the edge device using MQTT. And essentially how this flow works is we get our sensor data into the edge controller, which then passes this sensor data into our model. So this is our model. And this is passed through this component called the inference API. And what the inference API does is it takes in our data, it does some pre-processing on the data and formats it into a format that is accepted by a model. Then using this pre-processed input, it does inference on the model and then produces an output. And we do two different things with this output. So the first thing that we do is we store our output into a data store, inference output into a data store, along with the sensor data, as well as some system data like CPU, memory usage, things like that. And all this information will be made available through an internal REST API, which is consumed by our performance monitor right here. And then apart from that, we also have another component called a client application. And this is more of like an optional thing where we could allow developers the flexibility to do any additional operations on top of what is already being done on the edge device. So essentially, that kind of gives them the option to do any additional things that they might want with our inference results. So how did we implement our solution? So our solution consists of two command line tools. One is called the inference toolkit, which is responsible for packaging models with the inference API into a Docker container. And this toolkit is essentially used in our CI pipeline. And then we have our edge manager, which is running inside each individual edge device. And its purpose is setting up and managing the infrastructure and components of an edge device, which is basically everything you see here. So let me take you through what goes on in the inference toolkit itself. I hope this diagram is clear, but this is kind of a lot. Let me start from the left side here. So our inference toolkit, like I said, is a CLI tool, and it has two main commands called init and build. And with the init command, what you do is you set up the project template for our inference API project. And what you do with the build command is once you populate the template with what you want to do with this inference API, it takes everything, packages it into a container, and then pushes it into our model registry. So when we run the init command, what it does is, like I said, it produces a project template. And this template is written in Python, which is why we have this requirements file. And in here, as developers, we can put in all the dependencies of our model. Apart from that, we also have this manifest file where we give more information about the model, as well as these MQTT topics the model is expecting an input from, as well as what it expects to produce an output to. And the main component of this entire project template is this inference handler, which is a set of functions that are to be overridden by the developer. So we have a function called load model, which takes in our package models, and then it loads them into memory. Preprocess input takes in our input from our sensors and preprocesses it into the format that can run inference on the model. And infer, like the name says, it does inference on this preprocessed input data and produces an output. And with the output function, what we do is we basically take this inference output and reformat it into a structure that is expected by that is used by any end user or end application, or like a client application. So so we made a bunch of set of tools. How did we evaluate this solution? So the way we evaluated this was first thing we needed to do was we needed to come up with some kind of scenario where using this tool would make sense. And then we developed a simulation environment for it. And then what we did was, using this simulation, we evaluated the performance of the system and compared it against an existing commercial tool. In our case, this was AWS Greengrass. So to come up with a scenario, we first need to find a data set. So when we're finding a data set, we these are the things that we consider. We thought of using predictive maintenance because usually issues related to predictive maintenance need to be identified as quickly as possible. And then whatever environment that this is operating in, it needs to make sense that the hardware in this environment is capable of running machine learning inference. And of course, it wouldn't make sense if you could kind of do the same thing on the cloud. So it needs to make sense in such a way that this solution runs on the edge. So in the end, the data set we chose was this. It's an open data set to identify APS failures of Scania trucks. So APS stands for air pressure systems of Scania trucks. And this is some kind of more additional information about the data set. And the reason why we chose this data set was because it presents an ideal use case for a simulation environment that we would need to make. So because if there's an air pressure system failure in a truck, those kind of issues need to be identified pretty much immediately. And most computer systems in modern trucks are already capable of performing machine learning inference. And if it's a truck that's on the road doing transport, delivery, whatever, it might not always have access to the internet. So whatever computing or inference that you're doing, it needs to be done on the device itself, which is why we chose this data set for our simulation. And then using this data set, we came up with a prediction model. This is some information about the model. And this model was trained using the data set and then packaged into a container using AWS SageMaker pipelines. And yeah, that's how we made the model. And then what we did was we deployed this model into our devices and then did some testing. So what you see here is some results of load testing that we did. So what we did was we increased the number of requests per second, or the request rate, to the device, and calculated how long it would take to run inference and get a response from this model. So as you can see, at around this 150 requests per second, the performance kind of starts to deteriorate. And this was compared for both our solution as well as AWS. And you could see that AWS has a slightly better response time compared to our solution. Then we also measured our CPU usage over time. And since we could see that the performance kind of starts to go down at around 150 requests per second, we did our CPU usage at rates above 150 requests per second to see how this performance would go over time. So as you could see, like we compared this again with AWS, and both solutions kind of trend towards full CPU usage. Although again, you could see AWS has a slightly better performance, although our solution is not that far behind. So using these results, what can we say? So although you could see that AWS Greengrass did perform slightly better in comparison, it could be attributed to the fact that Greengrass it does not run on containers. It runs on its own on the hardware itself, which also comes at the cost of having to set up OS and application-specific libraries on each and individual device. Whereas if you're using containers, we have the option or the flexibility to work with more device-specific models in a more efficient manner. And also, we could notice that both solutions can handle requests up to around 150 requests per second, which is sufficient in most cases. And finally, in conclusion, the main objective of our project was to identify how we could integrate MLOps practices with edge devices using state-of-the-art tools and methods. And our solution was evaluated to have a performance that matches that of existing commercial solutions, with the added benefit of being open source and providing developers with the flexibility without relying on any third-party software. That's it. Thank you. Any questions?
Are there any questions? I have one question. Right now, the edge device is running by itself,
Yes.
So it has no control from the cloud. What kind of mechanisms can be implemented in order to have some kind of control, telemetry from the cloud, control from the cloud?
Yes. So yeah, at the moment it kind of runs on its own. So like you said, I think we were kind of talking about this earlier. One option is to have some kind of like an MQTT channel between the edge and the cloud, so that we could offer more communication. And other than that, we also kind of talked about this custom client application that developers could make. So essentially, there could be some kind of custom implementation in this client application where it could allow communication with any external networks.
Did you consider also to have like a mix between Greengrass and your solution? Use Greengrass. With Greengrass, you can deploy Dockers.
Yes.
So use the Greengrass as the deployment and the control from the cloud, and yours as the architecture.
Yes, there is actually a bit of what do you say, like a mix, because we were using AWS SageMaker pipelines. So ideally, SageMaker pipelines, if you're using with Edge, you should use Greengrass. But instead of using Greengrass, we kind of combined it with our solution.
Yes, because in addition, AWS SageMaker for Edge is going to be deprecated. So
yes,
nowadays you have to implement this in order to have a model for SageMaker in Greengrass.
Yes,
in the future.